I think we should be gathering to our seats now, folks. So there's plenty of room in front. So gather up, come forward, and we will begin. Where's Mike? Do you see my church? He's down there? Okay. So let me begin. And I want to welcome you to our Earth and Planetary Surface Processes meeting. This is, as you can see here, it's actually a combination of things. We will end with the sharp lecture, but first we have a little bit of business to share with you and talk about and do awards celebration, and then we'll have the sharp lecture. And so first, I'm Bill Dietrich, currently president of the focus group. Dorothy Maris is here. She's the president-elect, and somewhere out there preparing an interpretive dance, he said, was Greg Hancock. Can you stand up, Greg? There's Greg. Okay. So let's go forward and tell you about how this group is structured. This focus group operates on the volunteerism of a lot of people. We have an executive committee of about 20 members, and those committee members then populate these other committees: award committee, headed by Dorothy Maritz, the Fellows Committee, headed by Kellen Whipple, the Student Committee that Kieran Dunn has run, and apparently with great success yesterday, the Fall Meeting Program Committee that Kimberly Hill runs, and then the webpage, which I invite you all to look at, and if you have questions or things you'd like to add to it, contact either Marissa Palusis or Joel Scheingross. Could I ask all the people on the Executive Committee and who have populated this committee to stand so you can be recognized, because you make this place work. Thank you. Okay, some numbers. We have grown. This is the current number of people associated with our focus group. The total at the top, and then regular is what you'd call me, and student is the second category. So a total of 1748. That puts us 9th in order. That is, there's only 8 above us with larger numbers out of 23, which is a pretty substantial footprint. We are noticed. And it has consequences for us to communicate what we think is important at AGU. Please note this for the regular people in the audience, that the AGU is now committed to providing some support to any donation we make that's above $50. So if we can get roughly 500 folks or so to make a donation, 50 folks that make a donation of $50, then AGU will throw in another $1,000. And what do we do with that money? Everything we can. We support the young geomorphologist night. We support travel. We support the reception in the evening. So it's the currency that makes the place run. And so if you feel lucky and have 50 bucks in the pocket, please push the button on the web page and contribute. If we get to 57, we get some extra money. Okay, this is another metric of us, which, having watched this whole thing evolve, is pretty remarkable. We had 45 sessions and 37 oral sessions and 37 poster sessions and 982 abstracts. This might explain to you why there was some congestion, and it also may explain why you've actually probably lost some weight walking a mile to that one session you wanted to get to that was a mile away. But it's a sign that we are very engaged. And I think I congratulate you all for the commitment to come and contribute and share in your knowledge. 2 other comments. Gilbert Club is happening. And Nicole Gasparini, are you here? Can we thank you? I don't know if yes, oh, she's hiding. Nicole generously stood up and said, I will host it. And she's done a lot of work to make the Gilbert Club happen. There's 320 people coming. It's a great list of people, and I appreciate, with no boundary to it, the effort that Nicole's done to make this happen and continue what people refer to as our tribal gathering. I'll also add that it's already set up for, yeah, thank you. And then Monghung Huang and Colin Pressegard have already picked the room for Maryland. It's a few stops down the line, so there'll be a Gilbert Club number 35 with certainty next year. So please come, please engage, bring pop-ups and see your friends and bring your posters and we'll talk. I bring you 4 announcements from meeting with the AGU Council, which is people who, basically the president and the vice president of the focus group gets together and we talk about things AGU is thinking about, worrying about. Big news is we're now a section as of January. Everybody's a section, so you're all equal. So we are now the Earth and Planetary Surface Processes section, not focus group or sideline or something like that. So that's, I suppose, a promotion, but at least it's a new name, and that's rebranding, right? So there we are, we're a section. Second, annual meetings. Next year, DC. The year after that, San Francisco. The year after that, San Francisco, and then this is the big news. We've been told that they're intending to go to a 3-year rotation, anchor to San Francisco and going someplace else for 2 of the 3 years. You can take a deep swallow and think what you think of that, and if you have an opinion, email AGU either, what is it using the smiley face thing that you've got on your apps, what we didn't know about. Express your view. This isn't a signed, sealed, delivered thing, but it's likely to be this way. So we're going to be moving toward like the GSA model. Okay. This is 2 more important things. In 2019 is the AGU Centennial, and AGU is seeking creative ideas to celebrate, and they really are seeking. If you have ideas that you could think would be cool to do at the AGU session, particularly in San Francisco, but they're actually going to start rolling the drums out in 2018 in DC because it's in DC, bring them forward to us, and we'll communicate to AGU. The people have talked about field trips, they've talked about union sessions, they've talked about demonstrations of public. They've talked about people in their home countries doing something if they don't come, or during the year. We don't have to wait for the AGU session. If someone wants to start some kind of series of field trips in Spain or something like that, or in Alabama, no, California, you can do that. And with the encouragement of AGU, some way to express the enthusiasm of science and its value to knowledge and its value to society. There's money in the waiting to encourage you to do that. So think of ways to engage the public this way. Last statement is a little more local. In 2018, May 2018, it will be the 100 years since G.K. Gilbert died. And so we're looking for ideas to celebrate his anniversary in the fall meeting of AGU. And one idea that's already been kicked around is to have a union session on that with some perspective of, where have we been, where are we going. But we welcome ideas of any kind on the suggestion of doing something to recognize such an influential person in our field. Okay, one other thing we must do is to thank Jim Pizzuto, which I think he's here. Where's Jim? Back there. Jim was the past president, and he remains a continued force at AGU because he's on a governance committee that is affecting who governs us and the decisions made. And he's given us a real voice in this community, and he's been a great leader and a very generous person. So thank you, Jim, for all your help. Okay, that's business. Unless I see any hands up saying you have something you would really like to tell us in the business mode, we'll go to the celebration mode. Anything? Okay, this is semi-business, but it's still celebration. We were fortunate enough to get three folks to celebrate this year, 2 receiving AGU Fellows and 1 the McElwain Award. So Pat Weiberg and Greg Tucker each were selected for becoming an AGU Fellow, and these are the celebratory pictures with the gigantic face next to the small body. And the McElwain Award is Mike Lamb. If the 3 of you are here, could we stand up and at least applaud you? If you're here, if you're not, you're off having fun. Is anybody here? Okay, now we come to the awards. And we have 2 that we recognize, the G.K. Gilbert Award and the Leopold Award. And they have kind of an age stratigraphy to them because the Leopold Award is defined as young. But the Gilbert Award is not defined as really old. It can be anybody who's made these contributions, which is recognition of sustained and outstanding contributions to Earth and planetary surface processes, and has promoted an environment of unselfish cooperation in research and the inclusion of young scientists into the field. So we very much welcome nominations. And so if you feel inspired by someone you've interacted with, papers you've read, that you feel strongly influenced the field and your own thinking, and it's been an inspiration to you, consider making a nomination. This is how we go forward. This was the intent, was to honor our colleagues who have done so much for us. Okay, so we move to our first, the first award of the night, which is to honor Mike Church. And Mike is at the University of British Columbia, and I think he's known to virtually everybody. I think of him as our leading fluvial geomorphologist. Curiously, his landmark research for his dissertation, which received the Kirk-Bryan Award from another organization, but failed to get him a PhD. You are free to ask him how that works. Much of Mike's effort has been devoted to the study of gravel-bedded rivers. And I won't list all the accomplishments. I'll point to things that people so frequently go to, which is the methods for sampling the bed, for quantifying bedload flux in big, challenging rivers, and for mapping and exploring bed surface sorting by a variety of mediums, including granular mixture properties. But importantly, he has devoted considerable effort to improve river management. He's given that a big effort, and that's very important. But I want to add 3 comments that came from the letter of recommendations that are somewhat personal, and don't often come into these statements in front of the audience, but I think portray another aspect of Church that Mike Church that I think is important. The first one says, he has, by dint of his intellectual creativity and his devotion to obtaining high-quality data, elevated scientific standard of river studies. The second says, serves as the conscience and tutor to those in river science. And the third has been a figure who, throughout my career, has inspired me to push a little harder and think a little more deeply. I share all these experiences. I was a grad student who went to visit Mike and sought advice. I've read his papers. I've got advice from his papers. I've had dinner with him and got further advice. He's been generous through his whole career, and I personally benefited from it. So, Mike, it's time to come and embarrass yourself.
I'm apparently free to say a few words. Better? There's actually 4 things I want to say. First of all, this. Oh, okay. Well, whatever works. Okay. Can you hear me at the back? The first thing I want to say is that this award means a great deal to me. I think the most important awards one might receive are the ones from one's immediate professional peers. And this is an award from my immediate professional peers, so thank you very much. The second thing I want to say is to thank those people who made this possible. I don't even know who you are, but I'm thankful for your somewhat naive faith in the value of my contributions. And all I can say is I'll continue to try and justify your good faith by continuing to do things well. I'm not sure how long I can sustain that. I'm getting on, you know. And I've noticed recently that editor Buffington is getting a bit more severe in his judgments about my papers. But we'll try. The third thing I want to say is the really important thing. M-Church is actually just a corporate logo for 10 generations of really inspired graduate students. The science that sort of popped out of M-Church and Company really is the science of my students. And so this award, this G.K. Gilbert Award, is really an award to about 10 generations of students. There's about 60 of you. Some of you are sitting out there. I'm not going to name any of you because to name a few would be unfair to the others, and to name you all would get me kicked off this stage very quickly. And the last thing I'd like to say is this is the American Geophysical Union, and I'm not an American. And the remarkable thing about that is that there's absolutely nothing remarkable about it at all. The American Geophysical Union has been a beacon and a guide and an inspiration to all of us who do geophysical science in all its forms. Over the length of my career, it has notably broadened the boundaries of what constitutes geophysical science to include just about everything in environmental science. And that's a tremendously valuable service, because we need that if we're ever going to solve the environmental crisis that we face today. Furthermore, the American Geophysical Union has consistently attracted all of us from everywhere in the world, helped us forward, found mentors for us, constituted a forum for us to report our results and to talk to each other. It's an inspiration to all of us who do geophysical science, and indeed it's an inspiration because it's an example for the way science should be done. It's the way most of American science is done, and I just want to say thank you, AGU, for that opportunity and for the work you've done. And thank you for this award.
Okay, so now we go to the Luna B. Leopold Young Scientist Award. And this is what it's for. Given annually to one early career scientist, no more than 5 years post-degree, in recognition of a significant and outstanding contribution that advances the field of Earth and planetary surface processes. And once again, I encourage you to look to your mentors, your friends, the people you know have had a remarkable impact in an early career, and recommend them to us. We want to recognize people who've done a lot, and we're doing this today in a really nice way. The awardee this year is Isaac Larsen, and don't look at the name, at the University of Massachusetts. And he's made, for a young person, he's made a number of distinctive contributions on the topics of post-fire erosion mechanisms, on the nonlinear increase in landslide erosion rates on hillslopes steepening, landslide erosion rates as hillslopes steepen, very rapid soil production rates, something quite interesting to me, and the reevaluation of the size of the Missoula megafloods. All the recommenders both expressed enthusiasm and admiration for his accomplishments, and as it records the breadth of his interests and his talents. And so we, again, congratulate Isaac Larsen for becoming our Luna B. Leopold Young Scientist Awardee in 2017. Please come forward. So you know he gets two things. He gets an award for the Leopold Young Scientist, and he gets a sharp lecture. And you have to hold them while you talk. So set them down, and we have to find your thing. So let's see. How do we do that? We have to cancel one of these. Here. Larsen. Open this one. So you know that the one we're picking says, open this one. So we're waiting for it. It says, open this one. And I was thinking, does it make you smaller or bigger?
It's an exciting time to be a geomorphologist. The scientific approach ushered in by Luna Leopold and his colleagues continues to break new ground, spurred by the wealth of new tools that enable us to answer questions that could only be asked in decades past. Like Luna, I had the good fortune to work on a wide range of topics along my early career path. And on that path, I've had the pleasure to interact with numerous mentors who shaped the scientist that I am today. Among those, I'd like to thank the faculty at Carleton College for introducing me to the joy and the challenge of interpreting the Earth. Jeff Strasser for an eye-opening summer of research in Alaska where the seeds of an academic career were first planted. Jack Schmidt for instilling his unwavering commitment to scientific stewardship of Earth's landscapes. Joel Pedersen for introducing me to the challenge of grappling with landscape evolution on timescales beyond what I could observe. Lee McDonald for his steadfast support and often brutally honest feedback that turned me into a writer. John Stone for unselfishly sharing his exhaustive knowledge of cosmogenic nuclides. Dave Montgomery for modeling a scientific worldview that I can only aspire to. And Mike Lamb for profoundly expanding my horizons with new landscapes and by sharing his quantitative vision. Thank you, Bill, for those kind words, and thank you, Josh Roaring, for nominating me for this award, and to all of those who supported my nomination. Much of the research that brought on this award has involved colleagues from around the world, and I cherish my friendships with my many collaborators. And finally, I cannot thank my family, my parents, my wife Krista, enough for the love and support, and our sons, Carl and August, for the joy that they bring my life every day. I am humbled and honored to be receiving the Luna B. Leopold Young Scientist Award, and I thank you all for joining me today to celebrate Luna's legacy and for making this an exciting time to be a geomorphologist. The title of my talk is From Tectonics to Tractors, New Insight into Earth's Changing Surface. And it's a broad topic, so I'm going to start with a broad statement, and that is that investigation of the physical and chemical processes that act on Earth's surface has advanced our ability to interpret our planet's past and predict its future. And people in this room have made great progress on many questions, including what is the nature of linkages between climate, tectonics, erosion, and topography? How does the transformation of material in the critical zone influence global biogeochemical cycles? And what do erosional landforms and sedimentary deposits reveal about the history of Earth's environments and those of other planets? And finally, to what extent has Earth's surface changed during the Anthropocene? And what are the implications for the habitability of our planet, among many others? And this progress has been driven, at least in part, by new tools that allow us to interrogate Earth's surface with increasing detail. And those include cosmogenic nuclides that allow us to measure rates of erosion on timescales relevant to landscape evolution and to determine the timing of singular geomorphic events. Numerical models that allow us to apply theory to try to understand processes over timescales beyond what we can readily observe. Satellite imagery that allows us to track Earth's changing surface on ever-increasing spatial and temporal scales. And finally, digital topography that allow us to relate process to form. And my goal for the rest of this talk is to highlight how linking these set of questions with these tools provides new insight into Earth's changing surface. I'm going to address 4 topics in this talk. The first, asking the question, how do landscapes respond to rapid tectonic forcing? Second, how do weathering rates respond to high erosion rates? Third, how big were Candian carving floods in the Channeled Scablands? And finally, how much topsoil remains in Earth's most productive agricultural landscapes? I'm going to start with tectonics here in the eastern Himalaya and ask the question, how do landscapes respond to rapid tectonic forcing? And I'm going to start with an observation. And that observation is that erosion rates increase non-linearly as slope angles increase beyond a threshold value, as shown in this work by Montgomery and Brandon. And the question is, what is the physical mechanism that underlies this relationship? And the model that's been proposed to explain this is the model of threshold hill slopes, which states that landscapes respond to high rates of bedrock uplift and river incision by steepening to a maximum stable angle. And so if we imagine a landscape schematically with a spatial gradient in rock uplift rate. It's the vertical component of tectonics. According to this model, rivers will respond by increasing the rates of incision on their bed. And since rivers set the boundary conditions for hill slopes will respond by increasing rates of erosion. But the topography responds somewhat differently, not just a monotonic increase. At low uplift rates, hill slope angles are low, and they increase up to some angle that's set by the strength of hill slope material. And beyond that, any further increases in rock uplift and river incision rates are the response of the landscape was more landslide erosion rather than a steepening of topography. And so adjustment of landslide erosion on hill slopes steepened to their threshold angle is the key mechanism by which landscapes respond to river incision and rock uplift. But there have been no tests of the threshold hill slope model using landslide erosion data. And why not? It's because quantifying landslide erosion rates is difficult, as I'll show in a few slides. And landslide erosion records are inherently short-term. They're limited by the time period which we have satellite images or aerial photos, which are really decadal timescales. And given the stochastic nature of landslide triggering events, it's unclear whether measuring landslide erosion rates over those timescales reveals any information about landscape evolution. But the threshold hill slope model does yield 3 testable predictions. The first is that landslide erosion rates spatially track rates of river incision. The second is that landslide erosion rates increase non-linearly as hill slope gradients approach the threshold angle. And third, if a landscape is in steady state, then landslide erosion rates should be spatially correlated with rates of rock uplift and exhumation, which are by definition equal to one another if a landscape is in steady state. So the study site for testing these predictions is here in the eastern syntaxis of the Himalaya. The Yarlung Tsangpo River drains the southern part of the Tibetan Plateau and then turns to the north and then slices through the Himalaya, where it then becomes known as the Brahmaputra River, as it flows through the Yarlung Tsangpo Gorge between the two 8,000-meter peaks of the Namche Baro Massif. This is a site of focused erosion, crustal deformation, and metamorphism. It's been termed a tectonic aneurysm. And it's been estimated that half of the sediment yield from the Brahmaputra comes from just this 2% of the watershed area. Now, why this landscape? In many ways, it lends itself as a natural experiment for testing landscape evolution models. We can see from this photo that there's abundant evidence for landsliding in this landscape. Additionally, stream power data from Finnegan and others suggests that bedrock incision rates vary spatially by 4 orders of magnitude throughout this region, with very high values of stream power within the heart of the Tsangpo Gorge and lower values in the periphery of the landscape. Additionally, bedrock mineral cooling data suggests that exhumation rates vary spatially by 2 to 3 orders of magnitude through this landscape. And so what this map is showing is the locations of samples for bedrock thermochronology. And each of these symbols represents a different system: apatite fission track, zircon, uranium, thorium, helium, zircon fission track, and biotite, argon, argon. And the key to this map is that the larger the symbol equals the younger the cooling age. And so what you can see is that there's a clustering of very young ages right within the heart of the Tsangpo Gorge. And what I've done here is just outline and draw an envelope around the area that's exhuming the most rapidly at rates in excess of 2 millimeters per year. Additionally, this is a very steep landscape. So the Yarlung Tsangpo River is flowing here at about the elevation of the Tibetan Plateau, and as it makes its bend through the syntaxis, it drops nearly 2 kilometers before flowing into India. And throughout this region, the landscape is very steep. So the modal hill slope angle in the area that's exhuming most rapidly is 39 degrees, but in the rest of the landscape that's exhuming much more slowly, it's only slightly lower, 37 degrees. And this is very similar to the observation by Burbank and others in the western syntaxis that showed that hill slope angles were practically invariant despite large variability in exhumation. And so this is a landscape where there's abundant evidence of landslide erosion, high spatial variability in both stream power and mineral cooling ages, and spatial uniform slope angles. So if there is a place where the threshold hill slope model could be tested with landslide erosion data, this potentially is it. And so to test this model, I did a lot of landslide mapping, mapping landslides in the subalpine areas of this landscape over an area of about 10,000 square kilometers. So here, mapping only in the subalpine areas because the disturbance of vegetation allows the landslides to be identified. And I generated 2 landslide inventories, one that I call a pre-1974 landslide inventory that's based on mapping keyhole spy satellite images from the 1970s that have about a 4-meter pixel resolution, and a second inventory based on mapping on Aster and Landsat images with 15-meter pixels that ranged in time from 1974 to 2007. And I mapped thousands and thousands of landslides. And what I want to have information on is landslide erosion. And so I need a way to turn those mapped landslide scars into an erosion rate. And to do this, I turned to empirical scaling between landslide volume and landslide area. And using a compilation of about 400 measurements from the literature, specifically from the Himalaya, determined a scaling relationship where the volume of a landslide scales to the area raised to about the 1 1/3 power. And I used the scaling to determine landslide erosion rates by summing up the total volume of landslides and dividing that volume by the area over which those landslides occurred and the time period over which those landslides occurred, and use that information to assess spatial relationships between landslide erosion rates and stream power, hill slope angles, and exhumation rates. This is one of the results. So this is the pre-1974 landslide map, where each of the red polygons represents one of over 15,000 landslides. So this was a non-trivial data set to generate. And we estimate, based on the time it takes to revegetate the landslide scars, that these occurred over a period of about 3 decades. And if we then turn this landslide map into a map of landslide erosion rates, averaging erosion for these 10 by 10 kilometer squares, and again, omitting the high alpine areas or the floodplains that lack hill slopes, we get a map that looks like this, where the warmer the colors indicate the higher landslide erosion rates. And what you can see from this map is that there's a spatial coincidence of the highest rates of landslide erosion within the area that's exhuming the most rapidly. This is the 1974 to 2007 landslide map. Here, each of the blue polygons represents one of over 500 mapped landslides, the difference being the larger pixel resolution. And here we know exactly when the time period over which these landslides occurred, because essentially we're mapping all the landslides that occurred after the keyhole images were acquired. And again, if we turn this map into a map of erosion, we get something that looks like this, where again, there's a spatial clustering of high landslide erosion rates within the heart of the Sangpo Gorge, where exhumation rates and stream power are greatest. Now, if then use this information to test the predictions of the threshold hill slope model, on this figure I'm showing the landslide erosion rate as a function of stream power, and there's a modest but very significant positive correlation between the two. And this result effectively validates the first prediction and demonstrates that landslide erosion rates and river incision rates are spatially correlated. This figure is showing landslide erosion rate as a function of mean hill slope angle for those 10 by 10 kilometer grids. And what you can see is that where hill slope angles are low, landslide erosion rates are low. But when slope angles increase to near the friction angle, about 32 or 33 degrees, we observe that there's a nonlinear increase in erosion rates. And so this finding validates the second prediction of the threshold hill slope model, showing that landslide erosion rates increase nonlinearly with slope. In this figure, in each of these panels are showing landslide erosion rate as a function of exhumation rate for the 4 different thermochronometers. And for those systems with the lowest closure temperatures, the apatite fission track, the zircon, uranium, thorium, helium, and the zircon fission track, we see weak but significant correlations between the decadal scale landslide erosion rates and the millinyear time scale exhumation rates. And this result we interpret to validate the third prediction, demonstrating that landslide erosion rates and exhumation rates are spatially correlated. We don't observe a significant correlation for the biotite argon system, and these are the system with the highest closure temperature, and so these rocks are coming from on the order of 5 kilometers depth to the surface. And if erosion rates are a function of topography, which I demonstrated on the previous slide, what this might be indicating is that over the time scale it takes the rocks to come from 5 kilometers to the surface, that the topography is being rearranged. And so the answer to the question of how do landscapes respond to rapid tectonic forcing is that adjustment of landslide erosion rates on hill slopes steepen to their threshold angle. And we find that in the eastern Himalaya that landslide erosion rates are spatially correlated with stream power, which is a proxy for river incision, and exhumation rates, and that landslide erosion rates increase non-linearly with hill slope angles. And these findings effectively close the loop on validating the threshold hill slope model of landscape evolution. Now I'm going to turn to another rapidly uplifting and eroding landscape, in this case the Southern Alps of New Zealand, but instead of focusing on broad-scale spatial patterns of erosion and tectonics, I'm going to shrink down the scale to that of a weathering profile of soil forming from bedrock, and ask the question, how do weathering rates respond to high erosion rates? And there are many reasons to ask this question. One is that the answer has implications for understanding the geological carbon cycle. And so the form of the coupling between erosion and weathering has implications for whether mountain uplift is linked to the onset of ice ages and Cenozoic cooling as proposed by Chamberlain and revived by Ramo and Ruddiman. And in their model, uplift drives an increase in erosion, which comminutes rock and increases surface area, which increases chemical weathering rates. Some of that chemical weathering occurs via silicate weathering by carbonic acid, with the net result of CO2 drawdown by making carbonate rock in the oceans that sequesters that atmospheric CO2 for geological timescales, resulting in global cooling. The question is, what is the form of the coupling between erosion and weathering? Because it has to exist to get from uplift to cooling. And I've just shown schematically in cartoon form on the y-axis the weathering rate or the chemical denudation rate, and on the x-axis the erosion rate or the physical denudation rate. And the question is, what is the form of this coupling? Measurements from soils suggest that this relationship is linear, designated by the black curve. Measurements from rivers suggest that it's a nonlinear relationship, shown in green. And theory for soils, based on some very nice modeling work done by several groups a few years ago, suggests that the form of the relationship is hump-shaped, where there are low weathering rates, where erosion rates are low. They increase to some maximum value, and then decline as erosion rates increase. And this is due to an assumption that at high erosion rates, the thickness of the soil thins such that the residence time of minerals within the soils declines. But there are very few measurements at high rates of erosion to evaluate what's actually happening. And so I went to the western Southern Alps, here in the landscape between the Alpine Fault and the main divide of the Southern Alps on the South Island of New Zealand. And I went to this landscape because it's a very rapidly eroding landscape. Numerous data sets suggest that uplift rates, exhumation rates, and erosion rates are as high as 10 centimeters per year, or 10 millimeters per year. So here we're looking at a section through the center of the South Island. This is the Alpine Fault, and these are contours of rock uplift rate. And in the landscape just adjacent to the fault, they're on the order of almost a centimeter per year. And so this is a place where we know the landscape is eroding rapidly, and we can assess how weathering rates are responding. The field sampling involves the collection of 22 soil samples from ridge tops. So we're again looking at the center part of the South Island. This dashed line is the Alpine Fault. The main divide of the Southern Alps runs right across here, and with my colleagues from New Zealand collected samples from these boxes that are outlined in these colors, and you can see them down here, and we collected those samples along the ridge tops. And the work was done on a shoestring budget of $5,000 and a plane ticket from NSF during the New Zealand winter. And it involved crossing big rivers in small metal baskets, getting dropped off by helicopters on the tops of mountains and hoping they came to pick us back up. In reality, that didn't always happen, and so oftentimes we would have to get on the radio and call the helicopters in through the clouds. And when we were in the field, sometimes we had to crawl through the vegetation because it was so dense we couldn't walk through it. And we collected soil, and at the end of it all, my knees really hurt from carrying all that soil back up to the ridgetops to get picked up, and I shipped a few crates with about 600 kilos of soil back to the US, crossed my fingers to hope the boat made it, and in this case it did, and the reward was lots of mineral separation because those 600 kilos of soil contained just a few % quartz. We separated beryllium from the samples in John Stone's lab at the University of Washington, and at the end of it all, you get a few millimeters of beryllium hydroxide here in the end of a 15 milliliter centrifuge tube for scale, and send those samples off to Lawrence Livermore for AMS measurements. And it's a lot of work, but it's all worth it. And what we get from this information is the soil production rate, or the total denudation rate. That's the sum of both the physical and the chemical components. And we then use the chemical depletion fraction method of Reby and others, where we determine the chemical component from the total denudation rate by measuring the enrichment of an immobile element, in this case zirconium, in soil relative to bedrock, and then by subtraction determine what the physical component is. And what I'm showing in this plot of chemical denudation rate versus physical denudation rate are all the prior measurements that have been made using this technique. And I thank all the folks in the audience who have done this hard work. The question is, what happens when we go to higher physical denudation rates? And here are the results from New Zealand shown in blue. And what we can see is that there is no evidence for a rollover or a hump-shaped function. And when we fit a regression through this data, we see that the slope is within error of 1, suggesting that there's a linear relationship between physical denudation rates and chemical denudation rates. And the question is, why don't we observe a hump-shaped function or a nonlinear function? Well, in this landscape, hillslopes maintain a soil mantle even at high uplift and erosion rates. And so that soil mantle provides an environment where chemical weathering can occur. Why are the soil production and weathering rates high relative to other landscapes? For one, it's an extremely wet environment. In the area we were working, mean annual rainfall rates were as high as 10 meters per year. The rock is also weak. It's schist that's tectonically fractured, and we see abundant evidence for erosion of the rock by vegetation. So what you're looking at in this image is about a 10 centimeter thick slab of schist that's being pried off of the surrounding rock mass by plant roots. And we see this at all spatial scales. So these are millimeter scale roots growing within partings within the schist, breaking apart. And those roots are also pumping CO2 into the subsurface and increasing the production of carbonic acid. And the effect of the roots and also the decay of organic matter likely drives the very low pHs we see in the soils in this landscape, less than 4. And even though the soil production rates are high and the soils are thin, so the residence time of minerals within these soils are low, we see evidence for incipient podulization. So this white layer is essentially a zone of very intense leaching that's happening. And so this is an environment that's conducive to rapid weathering. And so what are the implications for these results for weathering fluxes? Well, the rivers draining the Southern Alps have extremely high calcium fluxes, some of the highest on Earth. And the Ca flux from carbonate weathering has been estimated to be on the order of 70 tons per square kilometer per year. And the calcium flux from silicate weathering is on the order of 30 tons per square kilometer per year. And the question is that we've been asking now is where within the critical zone does the calcium originate? And some very nice work by Robert Emerson and others have shown that carbonate weathering dominates in landslide debris, which is abundant in this landscape. And the question then we're asking is, where does the calcium derived from silicate weathering originate? And so with some new work led by my colleagues Andre Eger and Scott Henick, we've been trying to tackle this question by measuring water chemistry and looking at elemental ratios in soil water, in groundwater, and river water, and comparing those with the results from landslide seepage by Emerson and others. And what we find when we look at this in sodium calcium and strontium calcium space, where higher ratios are indicative of silicate weathering, the groundwater has low ratios that plot near the landslide seepage, indicating that carbonate weathering is dominating in the deep bedrock. Rivers fall sort of on a mixing trend toward soils which have much higher ratios, indicating that silicate weathering is dominant in the soils. And so the answer to the question of how do weathering rates respond to high erosion rates is that in the Southern Alps at least, soil weathering rates respond linearly, and the soil weathering likely drives the high silicate-derived calcium fluxes to the ocean in this landscape. And although we haven't quantified all of the effects of mountain uplift on the carbon cycle, the organic carbon side of things, the effect of sulfuric acid weathering, but the high weathering rates are at least consistent with the view that mountain uplift influences the geological carbon cycle and climate. All right, I'm going to transition to another landscape, in this case, the Channeled Scablands of eastern Washington, and ask the question, how big were canyon carving floods in the Channeled Scablands? And this is work I've done with Michael Lamb that started when I was a postdoc and is continuing today. And this is a Landsat image of the eastern part of Washington. And along the top of the image, we see the Columbia River and its main tributary, the Spokane River. And the story that's been worked out here, first by Bretz and by those who followed, is that during the end of the last ice age, the Cordilleran ice sheet advanced southward out of Canada. In the vicinity of Missoula, Montana, it blocked the Clark Fork River, which is off of this image, and that impounded Glacial Lake Missoula, which contained about 2,000 cubic kilometers of water. That ice dam failed catastrophically multiple times, and as it did, it sent enormous floods down the Columbia Valley, and work at the outlet of Glacial Lake Missoula and in the Columbia Valley by Baker and O'Connor and others have shown that these are truly colossal floods, some of the largest floods that have occurred in Earth's history that we know of. And in some places, those floods overtopped the valley of the Columbia, either because they were so large or because the valley was blocked by ice in other areas, and sent the floodwaters across the Columbia Plateau. And when it did so, it scoured the loess from the surface of the plateau and carved channels on the order of a few hundred meters deep into the basaltic bedrock. And it is these channels that will be the focus of the rest of my talk. And there are morphologically similar but much larger channels on the surface of Mars. And a question in both terrestrial and Mars research is, how big were the canyon carving floods? These canyons record paleo-environmental conditions that show eastern Washington and Mars had an environment much different in the past than today. And the morphology of these canyons potentially reveals information on paleo-discharge, which has implications for understanding mechanisms of abrupt climate change on Earth and understanding the history of water on Mars. But reconstructing discharge is challenging in these cases because both flow and topography co-evolve. And if one wants to quantify the discharge of a flood for a channel like this, denoted here as Q, you need to know information about both the cross-sectional area of the flow and the velocity of the flow, both which are a function of the flow depth, h. The question is, what is h? Evidence of high water is commonly used to guide paleohydraulic reconstruction, and in the Scablands, high water marks are common near the canyon brims. And so if the canyons are filled up with water to the high water marks, results in what we refer to as brimful flow. And in these canyons that didn't exist prior to flooding but were carved by flooding, this method produces a maximum possible constraint on discharge because erosion is not taken into account. And this is something that's been acknowledged by the previous workers on this. And the question is how much of an overestimation is it? And an alternative to this is that the canyon is sized progressively such that the high water marks were abandoned during canyon entrenchment, shown schematically here, such that their incision is like other canyons on Earth. And if this is true, then the brimful assumption might significantly overestimate discharge. How then can we constrain the discharge of an outburst flood? And to do this, we've borrowed a threshold stress model for channel formation from alluvial channels. And coarse-grained alluvial channels adjust their geometry so that bed stresses just exceed the threshold to transport sediment. And larger discharges produce larger channels and not extreme bed stresses. And although the mode of adjustment for bedrock channels may be different, they morphodynamically adjust to the stresses that are imparted on their beds. And it's been observed that many bedrock rivers maintain bed stresses that are very close to the threshold for sediment transport. And this is a figure by work by Phillips and Jeromack just showing that this a CDF of a bed stress. And this is the threshold for motion, and the CDF stacks up right against that, indicating that in these systems, any changes in stress result in a very rapid response of the bed in terms of changing the grain size. And we can characterize the motion of sediment in alluvial systems using the Shields criterion, where the threshold stress for motion of a particle of a given grain size is a function of the Shields number, which is the ratio of the force of the flow over the particle weight. And in alluvial systems, sediment moves when the value is about 0.045. The question is, what is the threshold for motion of jointed rocks, such as the entablature and colonnades of the Columbia River basalts that are common in the Channeled Scablands? Well, modern analogs indicate that jointed rock is quite mobile. These are field photos from work by Lamb and Fonstad at a dam release flood in Texas, where 8 meters of bedrock incision occurred due to block plucking and waterfall retreat. And what you can see in this lower image is that particles with diameters of several meters were moved by this flood, which had depths of only about 10 meters. So extreme flow depths are not needed to invoke the transport of very large caliber sediment. And flume experiments by Ellen Wohl and her students have shown that plucking via sliding, or the movement of blocks from a pocket of their surrounding blocks, can be the dominant mechanism by which blocks are plucked from the bed. And by resolving the forces on a block, Mike Lamb has determined a theory for predicting the Shields number for sliding. And it's a function of many parameters which can be either measured, inferred from material properties, or determined experimentally. And this figure shows values predicted by Mike's theory versus measured values from flume experiments. And the pertinent data here are in red and green, and they show that the theory nicely predicts when these blocks slide. And so based on this, we propose a threshold shear stress model for canyon formation. And the rationale is that given the mobility of bedrock blocks, the physics of eroding jointed rock is not unlike eroding a bed of non-cohesive sediment. And progressive incision occurs when shear stresses are at the threshold for erosion by plucking. And channels will adjust their morphology through bedrock erosion so that the bed stresses don't greatly exceed the threshold for block erosion. We test these models in Moses Coulee. So here we're looking at a part of eastern Washington. The area outlined colored in blue was inundated by late Pleistocene floods. And Moses Coulee is here in the northwest corner of the Scablands. It's about a 70-kilometer long canyon and was the site of at least 4 floods during the late Pleistocene. And most of what I'm going to focus on is this reach in the center part of Moses Coulee, This is a photo looking down into the canyon from the rim. This is actually a terrace, an abandoned channel, and the main floor of Moses Coulee is off in the background. The photo on the bottom is taken from the floor of Moses Coulee looking upstream. And our goal here is to simulate discharges that are predicted by both the brimful and the threshold stress models and compare those results against depositional evidence within Moses Coulee at two different sites. One in the northern part of Moses Coulee at the Great Gravel Bar. This is a large expansion bar in the lee of a bedrock protrusion. It's shown here in the field, this very large bed form with a road crossing it for scale. The second site is on that terrace I showed in the previous slide, where there's a large boulder bar here with a person for scale. And so our approach here is to simulate discharges as the canyon evolves. And as a field, we're not yet able to numerically simulate the evolution of realistic scablands topography. And so what we do here is to recreate topography by raising the channeled floor to 4 different bed elevations, shown here A through D, that are guided by terraces. So what we're looking at is a long profile of Moses Coulee. You can see there's a large nick zone in the center of it, and as that nick zone has retreated upstream, it has abandoned terraces. And we use those terraces to reconstruct these different bed elevations. And this is a crude reconstruction of the paleotopography, but what it allows us to do is understand how the hydraulics evolve as incision occurs within this study reach. And so our approach here is to route floods through this landscape using a 2-dimensional depth average shallow water code. We use one called Anuga Hydro, and then we extract data from the simulations that conform to both the brimful and the threshold stress models. This is a drone photo that shows that study reach. The areas denoted by the letters show the terraces that we use to reconstruct the topography. And essentially we start with a canyon that's filled up with rock, and then progressively lower that canyon floor until we get to the modern topography. And this is just what that looks like shown in cross-section here. And for each of those topographic boundary conditions, we iteratively simulate floods in 100,000 cubic meter per second increments across the landscape, and then allow the flow to evolve to near a steady state. So this is an example of one model run. We're looking at stage as a function of time, and at steady state, we extract key hydraulic variables such as depth and shear stress. And our approach to constraining the brimful model is very straightforward. The discharge where the flood stage reaches the high water marks is the brimful stage. And so we can see evidence of this in the field. This is Mike Lamb and my student Karen Lennox standing at an erosional scarp within the loess at the upper reaches of the flood. And so we can then extend that by mapping on high resolution aerial images. And this is a result for the brimful flow. This particular example is for the modern topography, which fills up to the high water marks in our study reach at a discharge of 3 million cubic meters per second. And if we just look at how the discharge evolves as the canyon floor incises in the brimful model, if we hold the stage at those high water marks, there's a monotonic increase in discharge from a few 100,000 cubic meters per second to 3 million cubic meters per second in the final stage of canyon evolution. Now I'm going to go over the approach to constraining the threshold shear stress model, and I'm going to start by just showing a movie that shows shear stress as a function of discharge. And what you're going to see is that at low discharge, the locus of high bed stress is in this region, but as discharge increases, the spatial locus of shear stress moves about. In this map, the white and purple are showing low stress, and the warmer colors, high bed stresses. And so we have high bed stresses here. Those are diminishing. The locations of high stress are moving to different parts of the channel. And this is all to just motivate our use of a 2D model rather than a 1D model focused on cross-sections. So what we first need to do is determine what shear stress is required to slide blocks in the channeled scablands. And so we use the theory that Mike has developed And depending on how we parameterize that theory, we've come up with a lower and upper bound of Shield's number for sliding. 0.053 as a lower bound, 0.085 as an upper bound. We rearranged the Shield's criterion to solve for the critical stress to move the material. And here we use a particle diameter of half a meter that we base on measurements of boulders done by many of the Caltech crew in the audience on some of the larger depositional bars in the Scablands, where we assume that these boulders started out life as basalt columns that had been rounded during transport. And this results in two sliding thresholds, our lower threshold of about 475 pascals and an upper threshold of about 750 pascals. And our approach then is for each discharge and topographic boundary condition, we determine the mean shear stress on geomorphic surfaces with different elevations in our study reach. So these smaller polygons along this cross section, and then we extract the discharges that conform to the threshold model. And this is an example of how we do that. So here we're looking at shear stress as a function of discharge. These horizontal lines show the thresholds for plucking via sliding. And for each site and bed elevation, we get two discharges. One where from the discharge that just exceeds the lower bound for sliding, and a second that exceeds the upper bound for sliding. And when we put all of this information together, we get a result that looks like this, where here we're looking at the evolution of discharge as the canyon is incising in time. And what we see is that there are, where the orange basically spans the range of discharges predicted by the two shear stress values. And we find that there's a narrow range of predicted discharges, which is consistent with a similar flood source, such as a self-dumping glacial lake, which has been proposed for Lake Missoula, where the ice dam fails when there's a threshold head of water pushing on it. And what this result also suggests is that canyon incision by plucking can occur at discharges that are much lower than brimful. So discharges on the order of a few 100,000 cubic meters per second as opposed to a few million cubic meters per second. And if we then look at how flood stage and topography co-evolve, in the initial stages of canyon incision, the flood stages predicted by both the brimful and the threshold model are similar, but as the canyon floor incises in the threshold model, the flood stage drops below the high water marks and abandons higher geomorphic surfaces. And this is a plot similar to what was shown in the previous slide, but instead shows water depth instead of discharges. And what you can see is that the discharges, or the depths predicted by the threshold model, are on the order of 50 to 75 meters. So still enormously large floods, but on the order of 100 meters lower than those predicted by brimful flow. And for the threshold model to, in effect, hold water, it has to be able to predict the inundation of bars within Moses Coulee. And what we find is that for the Great Gravel Bar in the upper part of Moses Coulee, it's overtopped at a discharge of 600,000 cubic meters per second, which is the same as our upper bound from our independent constraints from the threshold model for plucking. And so we don't need to invoke very large brimful floods to explain the macro-scale depositional bars in Moses Coulee. If we look at the second test site, the bar on the abandoned channel, we've determined the grain size here, and the D50 is on the order of 15 centimeters. And we calculated that D50 is mobile at a shear stress of about 120 pascals. And that's exactly within the range of values. And that occurs at discharges between 0.2 and 0.6 million cubic meters per second, which is right within the same range that we predict with the threshold stress model. We also have calculated the shear stress to suspend particles on this bar. And at brimful flow, the bed stresses on this bar are on the order of 1,700 pascals. And that can suspend particles on the order of half a meter in diameter. 80% of the particles on this bar have diameters less than half a meter, indicating that the bar couldn't have been deposited at brimful flow. And so the answer, how big were canyon carving floods in the Channeled Scablands? The Missoula floods were enormous by any standard, but Physics-based arguments indicate that discharges much less than brimful flow were capable of carving the canyon landscape on the Columbia Plateau. And this result is very consistent with a number of recent studies that have shown progressive incision of canyons, often via modest flows where rock is highly fractured. And this result has implications for interpreting the surface of Mars. So this is Robert Sharp. And Bob Sharp was one of the first to study the Mariner images that came back from Mars. And he wrote a paper called The Channels of Mars, on Mars. And in that he wrote, evidence for huge catastrophic floods is good in Mangala here and Aries channels, although the means of counting and storing water is a problem. And there have been several subsequent studies that have noted the incompatibility of producing brimful discharge with an aquifer flood source, which is the prevailing model for generating the floods on Mars. And the progressive incision and smaller floods predicted by the threshold model can explain the origin of the Mars outflow channels. All right. Now I'm going to move to the final question of my talk: how much topsoil remains in Earth's most productive agricultural landscapes? And you might think that this has nothing in common with the rapidly eroding places I've shown in the previous parts of this talk, but I assure you this landscape is eroding as fast as the Himalaya. And my group is starting up a big project on geochemical and field and numerical investigation of soil erosion in the Midwestern US, and while that's been ramping up, we've just been sort of dabbling in remote sensing, and this is all work that my PhD student, Evan Thaler, has been doing, and I'm just going to give some of the highlights of this, and I invite you all to visit his poster, which will be tomorrow afternoon. And this is a high-resolution satellite image from northern Iowa near the town of Clear Lake. That is the house that I grew up in, and what you can see when you look in the landscape around my house is that there is a distinct pattern of light-colored soils and dark-colored soils throughout the entire landscape. And in the field around my house, the light-colored soils occur on the hilltops, and the dark-colored soils occur in the hollows or in the lower elevation parts of the landscape. And as we look at these images from across the Midwest, we see a very similar phenomena in South Dakota. We see this in Minnesota. We see this in Nebraska. And we see this in Illinois. And I should note here that we've sampled soils in native prairies throughout this landscape, and when we sample soils on the hilltops, we see many decimeters of thick, dark, organic-rich soil on the hilltops. And so this is an anthropogenic phenomena, and that has been posed by several others before us. But the question we're asking is, how can we extract information about soil loss from space? And we've fortuitously come across the USDA's Rapid Carbon Assessment Project, and they've generously shared their data with us. And they've measured soil carbon, but also hyperspectral laboratory data, such as this from over 4,000 soil samples from throughout the Midwest, shown in these yellow triangles. And what Evan has done is he's used the laboratory spectra to develop an organic carbon index that's able to distinguish between A-horizon soils, or the topsoil, that's the fertile soil for agriculture, and the B-horizon soils, or the organic poor subsoils that are not as good for growing crops. And we've then applied that lab-derived index to high-resolution multispectral images from Digital Globe, thanks to Paul Moran and the NGA archive, and used those to map out the A-horizon extent and B-horizon exposure in plowed fields. And this is an example near Ames, Iowa, and what we can see is here, again, we have very light-colored soils and dark-colored soils, and when we apply the index that Evan has developed, we get a map that looks like this, where the tan colors are indicative of B-horizon soils, the dark gray-black soil is indicative of A-horizon soils, and this is developed with the USDA sample closest to this field. And if we just sum up for this area, 46% of the landscape has B-horizon soils exposed on the surface. So almost half of the area has completely lost its topsoil due to erosion. And the question is, how can we scale up? It's been known for a very long time that agricultural erosion is a problem. There have been thousands of papers published on this. There have been hundreds of thousands of soil erosion measurements. But one of the remaining challenges is the lack of methods for scaling soil loss estimates up across spatial scales. And our method is limited. Our imagery is limited in space. We don't have complete coverage. Even when we have images, often they're from the wrong time of year, so we're looking at corn instead of soil. And our carbon index is sensitive to what's on the land surface, so any type of conservation tillage that leaves residue on the ground, basically we can't use it. But what we do observe is that there's a spatial correspondence between B-horizon exposure and topographic curvature. So here, if we just look at the map of this carbon index, what we see is that there are these sort of diagonal lines that run across the field that indicate where the B-horizon is exposed. And this map is showing topographic curvature, where areas in red are indicating the convex parts of the landscape. Areas in blue are the concave parts of the landscape. And you can see that there are diagonal stripes of red or convex topography running across the landscape. And if we just overlay here the RGB image over the curvature, you can see that the areas with light-colored soils are associated with the areas of the most convex topography. And so we've repeated this exercise from the example near Ames, Iowa, to about 50 square kilometers of plowed fields. And what this does is reveal the functional relationship between topsoil loss and topographic curvature. And so what this plot is showing is curvature on the x-axis, and this is the mean fraction of topsoil loss. So it's just the percentage of pixels of a given curvature that have B-horizon exposed. And what we see across these areas, and so each of these green squares represents where these data come from, is that where the topography is most convex, the landscape has lost more than 90% of the topsoil, and that amount decreases as we go toward zero curvature, and then increases again. And so we have this functional relationship between curvature and topsoil loss. And we scale up by calculating curvature across about 350,000 square kilometers of the US using high-resolution LiDAR data shown in this area in gray. So basically our focus is on the formerly glaciated and former tallgrass prairie ecosystem. That's some of the most agricultural land in America and on Earth. And I'll just go to the answer. When we scale up, how much topsoil remains in Earth's most agriculturally productive landscapes? Well, in the Midwest, it's less than half. So in this figure, we're looking at a CDF of area. The black curve is showing just the total area of A and B horizon soils. And here we're using the USGS gap analysis data to only look at agricultural land use. And what we see from this CDF is that 70% of the landscape has convex topography. And of that total landscape, nearly 60% has lost the topsoil. And the question, why is that? It's because the plow is an extremely efficient agent of topographic diffusion. And soil transport by tillage is on the order of 2 to 3 orders of magnitude greater than that by natural processes. And the implications are that in the US, although models for tillage erosion exist, tillage erosion isn't considered in the models used for soil conservation planning. And so what we really need to do is rethink how we define erosion-prone topography. Even contour plowing like this, which is sort of a tried and true soil conservation method for reducing erosion by runoff, over time is going to move soil down the slopes off of the hilltops and degrade soil quality. And in the spirit of scientists posing solutions to environmental problems rather than just bringing bad news, we've done some calculations where if we were to change to soil regenerative agricultural practices that have been advocated by, for example, Dave Montgomery recently, we've calculated that we have the potential to restore about $4 billion in annual economic losses that occur due to reduced productivity that's on the order of $20,000 for the average farmer in the Midwest. So it's real money. And at the same time, we could sequester 1 to 2 decades worth of CO2 emissions from the US. So it's a win-win situation. We just need the policy incentives for something like this to happen. And I'm going to just wrap up with a quote from Luna Leopold in a paper he wrote called Land Use and Sediment Yield in a book called Man's Role in Changing the Face of the Earth. And it says, we may conclude that man's use of the land can have a marked effect on sediment yield. Because of the difficulties of measurement of the initial conditions, it is extremely difficult to evaluate quantitatively this effect. And Luna wrote this with respect to anthropogenic erosion. He could have easily wrote this about the difficulty in quantifying landslide erosion rates, soil production and weathering rates, or bedrock river incision rates. But due to the tremendous strides that this community has made in quantifying surface processes, I would hope that Luna would agree with my assessment that this is a very exciting time to be a geomorphologist. And with that, I just want to thank my colleagues at UMass, my students and postdocs there, all of the institutions that have supported this work, my co-authors on the research that I presented today, and everyone who has given me an opportunity or mentored me along the way. And thank you all.
We do have time for questions. That's the intent. There's microphones. Would anybody like to ask a question?
Thank you for that very interesting presentation. I'd like to comment and maybe inject a note of caution regarding the effect of weathering and the correlation of erosion and weathering with respect to CO2 drawdown. It's important to remember that weathering doesn't stop at the soil on the hill slopes. Once they get eroded, they become part of the floodplains where they are stored and redistributed over sometimes thousands of years. So the weathering continues there, continues in the estuaries, it continues even in the ocean. And all of that contributes to the CO2 drawdown. Yes,
I absolutely agree with you on that point. And certainly in places like the Himalaya or the Amazon, that's a very important effect. In New Zealand, where the transit between the alpine fault or the mountain front and the ocean is very small, it's probably a lesser effect, but certainly does take place.
Gary?
Okay, we're on the western side of the South Island of New Zealand, where it rains like shit all the time. And you've got high uplift rates, but your soil keeps pace with it. Now the continents have suddenly shifted massively, and ocean circulations have changed, and suddenly the west coast of the South Island has become arid. What happens next?
That's an excellent question. My expectation is that there would be a reduction in weathering rates. And it's a very valid point in that there is a strong climate dependence on this. When people ask me that similar question, I often say, well, the Himalaya, Taiwan, and much of Southeast Asia is not all that different from the South Island, where due to the effects of orography, there's an inherent spatial coupling between high rates of rainfall and mountain uplift. If we were to find a mountain range where it was very dry but rapidly uplifting, I would expect things to be different.
No.
No. Run.
You asked.
the coulee, the outburst flood erosion canyons, I've never been there, and you did show a bar there, but I was struck with how flat it looked from DEM topography. Are these really flat bedded, and how does that compare? I think of gravel bed rivers with highly diverse distribution of elevations in the bed. Can you comment on similarities or differences?
In the particular, there's quite a lot of relief on the bar. It maybe just doesn't show up in the image, but on the order of, for the smaller bar, many meters. For the large bar, tens of meters.
Yes, but for most of that channel, it looked like it was like there was only very few of those bars. Is that wrong?
Yes, there are not many. So they occur in different places, but often so there are areas where the bedrock protrusions shelter the flow, and so you have flow expansion that allows these bars to be deposited.
Another question about the Missoula floods. So do the lower estimated flood magnitudes imply longer duration floods or a different drainage mechanism where glacial Lake Missoula did not drain all catastrophically at once and maybe drain more slowly or partially drained? And does your work say anything about how we can think about the relative effects of magnitude versus duration in terms of large floods and geomorphic work?
Excellent question. I don't think the work actually revises how the ice dam formed and failed. But it really speaks to how those floods, when they overtopped the Columbia Valley, and what happened when they then went across the Columbia Plateau. And so we still don't have a good handle on whether there's no time implied in the results. So we could still have progressive incision occurring during a single flood, or that could have occurred during many floods. And that's still something to be worked out.
Yes.
I'm curious to know, with respect to question 4, how much you trust the relations between the spectral properties of the images and the A and B horizons versus the impact of tile drainage on drying soils and influencing the spectral properties of those images as well?
Yes, we initially we went down this road to make sure what we were seeing is really a signature of soil loss and not moisture, and moisture tends to basically change the total reflectance across all of the wavelengths up and down, and doesn't influence one band or another over the wavelengths that we're using. So we're fairly confident that what we're seeing is not a topographic effect of moisture distribution, but a soil property, really the iron content or the carbon content, which are inversely correlated.
Thanks, Isaac, for a wonderful talk. I have a question about the first part related to the landslides. So you have a pretty amazing data set. I know you worked very hard to digitize all 15,000 of those landslides. And I've wondered, since it's such an amazing data set, if you've parsed that data with anything else in mind. For example, looking at sort of style of failure, or mode or mechanism, or things like whether or not you see any spatial patterns related to, for example, possibly co-seismic landslides, or if you've thought about any of that, any of those kinds of questions when looking at that landslide data set.
So as a first cut, we haven't done much beyond what is shown here. I guess because I like pain, I've mapped another 10,000 landslides
Perfect.
that extend all the way down to the Himalayan front to try to understand whether the spatial gradient in climate, as you go essentially from the high orographic precipitation all the way up to Tibet, influences erosion rates. And as much as we can tell, it doesn't, and the tectonics are really what's driving things. I have wondered about the influence of the 1950 Assam earthquake, which is not too far from this area. And in the field, I've seen landslides that our guides have pointed out. This failed in 1950, and they have revegetated over the time scale between from 1950 to the images in the 70s. So I don't think we're detecting, at least to a great extent, a signature of that seismic event.
Okay, thank you.
I have one question that may reflect the speed at which you delivered your really very interesting talk, which is that you plotted weathering versus erosion rate, correct?
Yes.
And weathering was calculated as denudation 1 minus the zircon ratios. And it's plotted against erosion. It's plotted against erosion, correct?
Yes.
And erosion is denudation minus the weathering rate. So erosion is also denudation 1 minus the zircon ratio. So my question is there any chance that that's a correlation that's inevitable because you have sort of a small range of zircon ratios?
Can you repeat the question? It's really hard to hear. The question is the linear relationship between weathering and erosion a function of essentially a bias in autocorrelation because one is derived from the subtraction of one from the other?
Yeah, there's D on both axes.
Yes. That's a good question. I mean, I don't have any expectation that the zirconium ratios should occupy some limited space. So, I mean, they could have been 0.9, they could have been 0.1. They just happen to be about a third. And so if the ratios would have reflected different amounts of chemical weathering, I think we would have seen a deviation from that linear relationship.
I sense we have, so let's thank Isaac again for really great. We have two more announcements, folks. One is actually from your sponsor. Justin Lawrence is going to have a few words from NSF, our Geomorphology and Land Use Dynamics program manager.
Hello, everyone. I'm Justin Lawrence. I'm one of your program managers at the National Science Foundation. I want to assure you that the NSF considers your work to be important. The NSF Earth Sciences Division invests substantial resources in fundamental research and education on the processes that are of primary interest to your community. That is, those that generate and erode landscapes, create stratigraphy, and that couple the internal dynamics of the surface to climatic and tectonic forcings. I recognize that many of you are worried about potential budget cuts to NSF programs this year. Be hopeful. While we're not likely to see growing budgets in our programs in the near term, NSF will continue to have substantial resources and will need to continue putting those resources to good use. You can think of short-term budget cuts as speed bumps, and you can't let them wreck your career. Stay focused on your science and its benefit to society. Take strength from this great community. Remember that your work is very important, and things that are very important have a way of bouncing back when the political winds shift. From my position, I see this community making progress on some really tough social challenges. It is slowly, and at times painfully, becoming more inclusive of women and underrepresented minorities. However, large inequities continue to exist. There are only a handful of black people in this entire community, and that must change. Broadening participation is not just a numbers game. It's about including people in important work and helping them feel good about themselves and what they are doing in their lives. I can't tell you what an honor it has been to be entrusted with the work of an NSF program manager. I get to see all of your scientific dreams on paper and watch many of them come to pass. I was particularly excited to hear today's speaker, Isaac Larsen, who received his career award from the Geomorphology and Land Use Dynamics program that I manage. His work is truly inspiring, and I'm also inspired by all of you here in the audience. You produce the magic that makes the miracle machine work. Thank you.
And thank you, Justin, for being a strong voice for us at a time when we need that. So thank you again. Well, there's only one thing left. Turn over the card and see if you remember to sign up for the reception. And there should be enough food, but I think it's open bar for the first hour, so drink quickly because it's later you have to pay something like that. On the back side of your card, it says where it is, the Riverside Hotel. Thank you all for coming. Let's thank one more time Mike Church, Isaac Larsen, and the two fellows in the McElwain Award. Thank you all.